There you go. You can do it.
Okay.
Mm-hmm.
So this is going to be the last session of this 2-day tutorial. Hold on, because otherwise, guys, you cannot see it here. Just a moment.
Hold on just a second. Let me share the link with the participants.
Okay, so as I was saying, this is going to be the last presentation of this 2-day tutorial. We are going to be talking about first debugging, different options you have for debugging your code, and last we'll talk about profiling, how to profile your code, especially on HPC and parallel codes. So we are going to, for debugging, we're going to be talking about first a little bit of an introduction of what debugging is. And second, I'm going to present 2 different tools that we have here in our systems, GDB and DDT. So why to use a debugger? Well, that is a pretty easy question. If you have some code, you're going to have bugs. That's all. Some people claim that they are geniuses and that they don't introduce bugs in their codes. That's false. Everybody does it. Okay, there's nothing you can do about it. You're going to have bugs. The easy solution when you have bugs is just start using printfs or write to files and so on to try to help, to try to figure out why or where the bug is. And sometimes that helps, sometimes that is enough if the problem is almost trivial, but most often that is not enough, okay? Also, when you're using prints, writes, sometimes they are not very accurate because of the buffering of those instructions. So you might think that the code is crashing somewhere when actually it's not crashing there. So you need something that is more accurate than that. And profilers, debuggers help on that. And also, many times, errors are very difficult to find without a debugger. Typical cases is you would think what the samples that we're going to see here, if you have to find why you have a division by 0, those are kind of easy to find. But what's going on is just some intermediate result is not correct. And the intermediate result is leading to problems in the final result. Those are more difficult to detect, and that's where a debugger is helpful. Okay, so in any Linux, Unix machine, you're going to have at least GDB. GDB is the GNU project debugger. As I said, you have it in every Ubuntu or here in Stampede machine. This is the link where you have more information about it. It basically looks inside of a running program, and it will tell you what's going on. Okay, GDB can do 4 things. You can start your program. You start your program and you specify anything that might affect the behavior. It can make also your program stop on specified conditions. You can say, hey, I want my code to stop in this line I want it to stop if something happens. Once the program has stopped, you can check what was going on. You can check the values of the variables at that particular time. You can inspect anything you want. And you're also able to change things in your program. Okay? So you say, for example, this variable has value 2 and it was supposed to have value 4. What happens is I change the value to 4 and I continue. Is the result the expected result or not? If it's not, you have something else to fix, okay? So those are things you can do with GDB. And in general, you can do these things with any other debugger that many of the debuggers you can think of, okay? It's not that GDB is the most sophisticated one. What you have to do to use GDB is first to recompile your code. You want to recompile with -G and with -O0. Why -O0? Okay, Carlos was talking before about optimization, and he said, oh, you have to compile with O3, Xhost, blah, blah, blah. And it's true that when you want to run your code in a production environment, you have to compile with O3. You want to get all the performance that you can have. When you are trying to find problems, you want to compile with O0. O0 deactivates all the optimizations introduced by the compiler, so that the assembly code or the binary will look a lot like what you are writing in your code, okay? And -G flag will generate the symbol table, and it will provide the debugger with a line-by-line information about the source code, which is something that you need for debugging. Okay? Something else interesting is that you can load the source folder if the source folder is in a different folder. This is going to be required once you start debugging, because GDB needs to know, oh, this assembly code belongs to this original source code, okay? So there are 2 levels of control on GDB. One is the basic one. You run the code and wait for the code to crash. But of course, it only works if you have a code that is crashing. It's very useful because it will identify the line where it crashes and it will stop there. And once the code has crashed, since it will stop there, you can inspect and check the values of the variables involved in the computation at that particular time. Hopefully, the problem will be obvious and you will be able to fix it quickly. But that never happens, really. The other level of control is more advanced. In this case, for example, if your code is not crashing, you want to set breakpoints, and the execution of the code will stop at those breakpoints. At those breakpoints, you can analyze the values of all the variables in the program. You can analyze that data, you can specify, you can watch specific variables. So you can also check for the status of the stack at that particular time to inspect all the different frames that led to that particular portion of the code. As I said, GDB can be found in all the Linux environments, Unix environments, and that makes GDB very, very popular. Now, all I can say about it is that it is popular, but still it's not user-friendly to use. We are talking about a command line debugger, so no graphical user interface, no nothing. You have to run these commands to use GDB, okay? So if you want to run your code, you have to press R or type run. If you want to continue, you have to press C. If you have to go to the next line, you have to type S, and so on. And you have to learn these codes, okay, these commands. So not very nice. There are nice free GUIs that can work on top of GDB that are easy to install in any machine. I can recommend, in this case, DDT. It's a very nice graphical user interface that works on top of GDB or even IDB. And for small codes, it's actually really, really nice. Much better than any other, even commercial product that you can find for debugging. So this is an example of GDB In this code, you have it in Stampede in this part of our lab. You can see line 17 on the left, well, also on the right, there is a division. We are dividing 1 divided by x minus y. If you think about it, we have a potential problem there, which is when x and y have the same value. If they have the same value, we'll have a division by 0. Okay? And since in the main program we are initializing x to 5, and we are iterating over y, once y has value 5, this code will crash, right? This is a fairly trivial example. Usually, of course, your code is not going to be like this. But this is just to show you how these debuggers work. So the first thing you have to do is to compile, as I said, with -g and -O0. And let's say the name of this executable is a.out. Well, we just call GDB with a.out, and we run the program, okay? With the command run or R. After a few iterations, and really quick because this program is very short, GDB will show this error message. Program receives signal sig FPE arithmetic exception. And it even tells you that where it failed, lines 28, and it will show you the line. Okay? Well, once it has crashed, what crashed was your code. GDB is still running. If you type where, the command where, it will tell you in this case that you are at line 28 and that x and y, which are the variables involved in the specific calculation, have values 5 and 5. So if you have this instruction 1 divided by x minus y and x and y are 5, you can figure out what's going on, right? As I said, this is not the normal scenario for you. We wish that it was always like this, but it's not. Okay. Well, this is basically what I was talking about right now. So one thing of GDB is that you can print the value of basically anything that you have in any variable that you have in the code. With the command p or print, you can print in the first line x, which is a scalar data. You can print a vector. You can print each individual elements of one vector, consecutive elements of vectors, and so on. Okay. As you can see, not the nicest user interface, but still very useful. To the point where if you learn how to use GDB, you will even try to avoid other commercial products if you can. This is extremely simple, but extremely powerful and fast. Breakpoint control is critical. In the example that I show, of course, the code is going to stop because it has a problem. It has a crash in the code. But if your code is not crashing, and you want to look for specific values, specific variables during the execution, you want to insert breakpoints. This is like any other debugger in the market. So all you have to do is to use the command breakpoint, and then enable, disable to play with those breakpoints. The code will run until it reaches one of those breakpoints, and they will stop. At that point, you can print the variables in that specific frame. You can attach GDB to running program. This is very useful when you submit a job, and then you can connect to that node and attach GDB to that running process. To do that, all you have to do is GDB -p and pass the process ID. And you can also do attach. So this is the best thing for running production, for debugging production runs. So as a summary, as I said, this was going to be, GDB is quite complex, but we are not going to go into all the details of this. All you had to do, and this is the most important thing you can get of this part of the presentation, is that you have to compile your code with -G and -O0. Once you have that, you can start debugging your code, okay? The other debugger that we are going to talk about is DDT. We have DDT in Stampede. DDT is a multi-platform debugger that supports most or all of the MPI distributions, and it will allow you to debug at large scale, OpenMP, MPI codes with thousands of tasks, okay? It has memory checking, MPI message tracking, basically everything you can think of. One note here is just, even though DDT supports thousands of processes, when you are debugging parallel codes, you really want to find the minimal example that can reproduce the problem that you have. What I mean by that is that if by running in two processes, you can reproduce the error that you are experiencing with 2,000 tasks, then you want to debug with two processes, okay? It's going to make your life easier. That's it. Hopefully, even if you are able to run in serial, that's even better for you. So when you start DDT, it will show this window where you can specify the executable or the application that you want to run, the arguments that you want to pass to your application, and you specify the type of MPI stack that you are using, OpenMPI, Babbage, Intel MPI, whatever you have, and you specify the number of MPI tasks or OpenMP tasks or threads. You can even pass CUDA options if you are debugging something for GPU. Of course, you can do memory debugging and other advanced options. DDT by itself, we could be talking about it for hours, and we don't have that much time. So something you can do from DDT, or the way to use DDT in Stampede, is that you load DDT on the login node and you submit the job to the queue from DDT, okay? That is the typical way to do it. Unless you are in that remote node, maybe you submitted an interactive job using IDEP. In that case, you can start DDT in the remote node, and you have to remember that you are not submitting a job because you are already in the compute node, okay? In that case, you don't have to specify the queue, you don't have to specify the project or the work clock limit or anything like that. Once your debugging session is running, this is what DDT looks like, okay? You have on top of the window, you have the number of processes that you have. In this case, we have 16 processes. This is an MPI code. On the left, we have the source navigator, so you can go through the different files that you have in your code. The center panel is just your source code. On the right, you have the variables that are involved in this particular point of the computation and that you can evaluate. Also, the evaluation panel that I already mentioned, and you have on the lower panel you have stack view, input, output, breakpoints, etc. So it's basically like any other graphical debugger. If you want to set breakpoints, all you have to do is to right-click on a line number and set a breakpoint. That's all it takes. So it's very easy. Once you set a breakpoint, you continue your execution, and the code will stop there. You can switch between tasks or threads to check the values of the variables in those other tasks or threads. So, and this is very interesting because quite often, or normally, your code will be introducing the bug in one of the threads. It doesn't have to introduce the bug in all of the threads. So you want to inspect all of them individually. You have an array viewer that is quite powerful. compared to what you can get on GDB, this is much more nice. You can go through each individual value of the array easily in this case. Another interesting thing of DDT is the memory usage. When you enable this, DDT can tell you a lot about memory leaks. Although my experience with this is you are better off using Valgrind. It's a much more powerful tool for memory leaks than DDT. Okay, in Valgrind you have many more options and many more things that you can check, and it gives you the information that Valgrind gives you is much better than this one. Okay, because it suggests things that you have to fix. So as a summary of DDT, well, all you have to do to use DDT and Stampede is just you have to connect with X11 forwarding, so SSH minus dash X or capital Y. Then you compile your code, in this case with MPI CC minus G minus O0. You load the DDT module with module load DDT, and then just run DDT on the login node. That's it. Okay? So some conclusions of this session, or the debugging session, is that first, you always want to debug your code if, this is if, but this if is basically always, if the program is not correct. And this is going to happen. Okay, as I said, no one really writes a complex program that works at the very first time. If your code is hanging somewhere, you would expect your code to finish and it's not finishing. Maybe there is an infinite loop somewhere and you have to try to find it. And this is not easy to find. It's easy with the debugger, but without the debugger it would be pretty complicated. If you have wrong results, which is the worst case scenario, because wrong results are the most difficult thing to fix. If you have had to do this in the past, you already know that this is very tricky and can be a nightmare. But debuggers are here to help. Of course, as I said at the beginning, you can always use printf or writes or whatever. And I'm not telling you that you cannot use them. In fact, we all use those things. They are really handy when you're just really checking for things that you are guessing that are going on. But for big codes and big problems, debuggers will be more useful. So that was for debugging. If you have any questions, let me know. Otherwise, there is a lab session that we are going to do at the very end after the profiling session. Okay. So we move to profiling. Just in a couple of minutes.
Good.
So this is going to be the last presentation of this tutorial, of this 2-day training session. It's going to be about profiling. A very short introduction to profiling, because again, profiling is a very complex thing in the HPC world. So let's see. So I'm going to be talking about the different profilers or tools that we have here in TAC, especially in Stampede, like the command line timers, code timers, GPROF, IPM, Perfexpert, HPCToolkit, VTune, and Tau. Okay. This is the optimization process. Carlos already showed this picture before. The optimization process is an iterative process. It's application dependent and it has different levels. Compiler options that Carlos was already talking about, performance libraries, and code optimizations, okay? So you have to decide when you stop with this. You profile your code, identify the hotspots, modify your code, you check if you got any performance improvement, and based on that, you decide what to do next. And at some point, you had to stop. Unless, yeah, if you have all the time in the world and you really enjoy it, okay, go ahead. But that's not the case for the typical case for people. So you always have to decide where to stop. The basics of performance analysis is just you need to have control measurements of what you're doing. You need to have a very controlled environment. You have to, Carlos was also talking about this before, you have to, if you're using threading, you have to be able to ping your threads specific cores, and you have to be able to repeat that in a controlled way. Okay, one result is never enough to say how good your code is. You have to document everything. You have to save the code, the compiler and flags that you're using, the user inputs, the environment, everything you can think of, everything you might need in order to reproduce that run, okay? You have to, it's important, and I think we don't usually do this, but it's important to do it. You have to make everything automatic. You have to do scripts that run these tests, that initialize your environment, that collect the results, that print graphs, everything, okay? Because otherwise, you run this today, in 2 weeks' time, you come back to it, and you don't remember what you were doing. That's the reality. It's impossible to remember, okay? And control. It's very important. Don't let the operating system to decide how the process and memory affinity work. You have to control it. During these 2 days, we have seen many different environment variables that you can use to control process affinity, memory affinity. So you have to use all of those things. A very important thing when using Intel processor is that the floating point operation counts are not exactly correct because they count on issued instructions, and these instructions can be reissued depending on how the pipelines are in the specific moment of the execution of the code. And this applies to the Sandy bridge, Ivy bridge, and Haswell. And also the Intel Xeon Phi or mics do not have any means of measuring floating point operations directly. So any result you can get there is going to be incorrect. So in order to profile your application, you can use the most basic tool, which is the timers, and especially the command time, which is available on most Unix systems. It's very simple to use. You don't have to do anything. All you do is you run your code by typing time before your code. This will give you the time that it took for the code to run from the beginning to end. Easy, okay? Nothing else you have to do. Of course, the information that it gives you is not a lot, but you can get an idea of how your code is behaving. The next step is to introduce the timers inside of your code. This is useful if you just want to measure or time particular functions or methods in your code. Earlier today, during the OpenMP session, I showed you how to use OpenMP wall time function to measure time. This is the typical way of doing the same thing in C and Fortran. Compared to the OpenMP syntax, this is slightly more complicated. It's not that it's difficult at all, but it needs more instructions. The most basic profiler that you can have in any Unix system, the same way that you had GDB for debugging, is GPROF for profiler, which is the GNU project profiler. When you're using GPROF, you have to recompile your code. And you're going to have 3 different types of profiles: the flat profile, the call graph, and the annotated source. The flat profile it gives you, in a very short and clear overview, the most expensive routines that you have in your code. So you just have a look at this, at the report of the flat profile, and you immediately know which functions are the most time-consuming. In many scientific codes, you will usually have a kernel where most of the time is being spent. Unfortunately, there are other applications where 10 functions will take 10% of the runtime, and that's more difficult to see here, and it's more difficult to optimize. The call graph will give you the number of times that a function was called by other functions, and the number of times that a function is calling other functions. This is very useful to identify function relations. This suggests places where function calls could be eliminated. And in order to use GPROF, you have to recompile, as I said, you have to recompile your code. You are going to recompile with -g that we already know from the previous presentation. And we will also use, in this case, -pg if we are using GCC, or -p if we are using ICC. Okay? With that information, the profiler will be able to give us the profiling. All we had to do after compiling the code is just run it normally. So don't use GPROF or anything like that at that particular time. You compile and run your code the same way that you would normally run it. The only thing that will happen is that this time, your run will create a file called gmon.out, okay? Which is a weird file, binary file that you cannot see what's going on in there. And once you have it, what you do is you run GPROF, and you pass as arguments your executable and the gmon.out file, and you redirect that output to the file that you want. In this case, for example, to profile.txt. And in that profile.txt, you will have something like this. This is the actual output from GPROF. And this is the flat profile. As we can see here, we have on the left the percentage of the time spent on each function. We can see how 50% of the time is being spent on mat sqrt, 24.7 and 24.7 in matcube and syscube in this particular sample. And then you have main, which is only taking 0.6% of the time. You also have the cumulative seconds and the self seconds. The difference here is just self seconds is the time that is spent in that particular function. Cumulative one is the time spent on that function and all the functions called from this particular function. That's why you see here the main has a cumulative value of 4.94. Okay, so that means that your main code, the main method, ran in 4.94 seconds. it doesn't mean that it spent for almost 5 seconds in that function, because it actually only took 0.03 seconds in that particular function. Okay. That is what I was explaining right now. So if you see something like this, you know that if you want to improve your code, you have to work on those 3 functions. The one that is taking 50% of your time, and the 2 functions taking almost 25% of your time. You will, of course, try to start with the one using 50% of your time. A small improvement there will lead to big improvements in the performance of your code. This is the code graph. So immediately after the flat profile, this is what you will find in that file. Okay, and this shows that from main, we call CSSQRT. From CSSQRT, we call mat SQRT, then sysq, matq, bec SQRT, and so on. So this is what it will look like. This is what your code kind of looks like with main calling all those functions. If we keep looking into the graph profile and we go into mat SQRT, we also can see that it's called by CSSQRT, which is what this function says, this image is showing. We can keep going, and it also shows that it's being called by this other function here. So you have something like that. So once you are more or less proficient, you kind of know how to use GPROF. It gives you quite a lot of information, but it's still tricky to use. Another profiler that we have here in-house is Perfexpert. Perfexpert is developed by people here at University of Texas in Austin. It's easy to use and understand, and it's really great for quick profiling and for beginners. It will tell you the critical path that you have in your code, meaning this is the sequence of instructions that is taking most of the time in your code. And the great thing is that it offers optimization suggestions. And it's really cool because you run it, I will tell you in your code, in this file, in line 300, for example, if you change the order of this for loop, you will probably get a performance improvement. So it's really cool. The information that it provides is really, really great. Sometimes it's too much. You have to decide what is good information or it's not good information, but it's really worth trying. In order to use Perfexpert, you have to load first PAPI, then you have to load HPCToolkit, and finally Perfexpert. And all you have to do is just recompile your code with -G, that's all, okay? Not PG or anything like that, just -G. Then you run it with Perfexpert 0.1, which means that it will only show the functions taking more than 10% of the time. You don't really care about short functions. Then you pass your executable and the arguments to your executable, and that's it. This will give you all the information that I told you before. That information looks like this. In this part is telling us, well, the ratio to total instructions is giving us the floating point operations, the data accesses that we have. Is going to tell us the percentage of here from 0 to 100, the gigaflops as a percentage of the max number of G-flops that we can get. And then it shows some kind of a report that saying, based on what you could get on this system, your code is good, okay, fair, poor, or bad, okay? And this is a very visual way of seeing things. For example, here, based on the number of hits on LD2 cache, is telling us that our code is not bad, but that is really bad for L1 cache. And so on. So depending on your code, these symbols will change, and it will tell you how good or bad your code is. And this is also one of the suggestions that Perfexpert can make for you. I will tell you, well, these two loops, you can join them, you can put them together, and you will probably get better performance. This is something that maybe the compiler would do for you, but it's better if you even do it before the compiler does. There is an advanced Perfexpert Use, and you can find much more information in this link. Also, if you have questions or problems when you are running Perfexpert, you can submit a ticket to our ticketing system, and the Perfexpert debuggers or developers, they will be happy to help. Another tool that we have here is IPM, which is Integrated Performance Monitoring. This is it's a very quick and easy to use profiling tool. And that it's not going to give you the level of detail that Tau, we'll see that later, PAPI or HPCToolkit or even Perfexpert will give you. It's because sometimes you don't need so much detail, okay? If you just want a quick overview of how your code is behaving, you don't need all that information. The thing of IPM is that it's very easy to use. It's scalable, so you use it for MPI tasks, MPI codes. Has a very low overhead, which is very important. And it requires no source code modification. You just add the -g during compilation, and that's all, okay? It will produce an XML output, and you can parse this XML output to produce HTML pages. In order to use this IPM, you just load the IPM module. You have to export LD preload so that this lib IPM.so is always loaded before you run your code. And then you specify which kind of report you want. In this case, we want the full report. And once you've done it, all you have to run is just all you have to do is to run your code that you would normally use or do with IB-run in our system. So just IB-run, executable, and the arguments. Okay? Once you have the output, the XML output, all you have to do is to call this IPM_parse -HTML plus the source plus the folder with the data that you just generated, and this will create the set of HTML pages that you can go through. It also provides some text output, which is also very useful because the same way that GPROF, the flat profile, gives you a really quick overview of what's going on with your code. IPM here, you can already see that there are many calls to MPI broadcast, and that this call is taking 12.5% of the total execution time, okay? So you really want to check if you need all these broadcasts here. It's also that instruction itself is taking 60% of all the MPI time of this program. So again, as I said, the same way that the flat profile gave you a really quick overview, here with just with this information, you're able to see, hey, maybe there is something going on with my MPI broadcast in this case, okay? Maybe I don't need it that much. Or maybe you do. You're the developer, you know about it. This is how the HTML pages look like, which is basically somehow, especially this plot here is what you saw before in the text file, but it also gives you much more information, okay? It gives you the PAPI counters. If you know what they mean, that's great. You can try to think how to improve that, how to improve cache miss, how to reduce that, and so on. So with the techniques that Carlos was talking before in the previous presentations, you can work on that and try to improve the values given by this tool. Okay, this is more information about the MPI task. As you can see there, it produces a lot of information, and it's up to you to see which one is useful for you. Okay. This is a typical one, which is the communication topology or how each rank talks to other ranks in your MPI program. As we can see here, 0, for example, MPI 0 talks a lot to all the other tasks. Then only one talks to 0, so it's kind of a ring somehow. Sorry, not a ring, is kind of a master slave. So IPM is very good because it's really fast, but sometimes it's not the best because it's not going to discover anything new. But this also applies to any profiler, actually. The thing is that when you need really a lot of detail about your code and exact information about lines, you want to use something that gives you all the information, okay? And the information that it gives you coming from PAPI is very limited. If you want to find much more information from that, you have to use other tools. Also, Intel MPI has MPI stats within the MPI just during your execution, so you don't have to do anything at all. All you have to do is when you are running your MPI application, you set those two values, environment variables, I_MPI_stats equals IPM, and I_MPI_stats_file equals any file. And it will generate a profile of your MPI application in that particular file. And this is very basic, but it's really, considering the amount of effort that you're putting on getting this profile, is very nice. There is another tool very similar to this, which is MPIP, that we also have in Stampede. In that case, you have to recompile your code to use MPIP. And those were the basic tools that we have. And we also have other tools that we call advanced profiling tools that many times are difficult to install. They have many dependencies, and they require kernel stuff. They're really a pain to install, okay? But we have done it for you. We go through that trouble just for these things, so you don't have to worry about that. So if you're using Stampede or any other HPC machine, you're going to have these applications already installed, some of them. The most basic one is PAPI. I've talked about this one a little bit during this presentation already. It's very basic, and it's so basic that it's so basic and powerful that it's used by all the other profilers, okay? And when I say that it's basic, I'm not meaning that this is not good. What I mean by basic is just, it's so close to the hardware counters, performance counters. It's such a low-level thing that it has to be used by all the other applications, okay? If you really want to use PAPI, you better read the documentation and you try to understand what PAPI is doing. It's not easy to use, but it's extremely powerful. Another application that we have here is HPCToolkit. HPCToolkit, a good thing that it has is that it doesn't require you to recompile your code. And it's very scalable. So when running on many cores of running for a long time, you don't, it's not going to introduce a big overhead, which is something that you will see that many other tools do, that your code runs for 5 seconds and you run it with the profiler and it runs in 5 minutes. Well, HPCToolkit is not going to do that, okay? which is very nice. This is the typical overview of HPCToolkit. But as I said, all you have to do is you just recompile with -G -O3, and then you use the HPC run executable to run your code. IV run if it's in parallel. Okay. Once you've run your code, you can view the results by running HPC viewer and the HPCToolkit database that you created. With HPC run, since it's using PAPI, you can specify PAPI events. For example, the level 2 cache misses or whatever you're interested on. If you want to see all the events that you can specify, all you do is just HPC run -- list events, and will show you all the different events that you can use for this. And this is what HPCToolkit looks like. I'm not going to go through every single one of those elements, but this is probably the most important one, the hot path. It's basically telling us the sequence of functions that is taking most of the time in our execution. Okay, so you really want to have a look at that and try to optimize that. Okay, so it's very easy for you to find that out. Okay, I'm going to skip this, and we're going to finish with VTune. No, we have tau after VTune. So VTune is an Intel product, so it works really well with Intel. Big surprise, right? We have it available in Stampede. You have to do is to module the VTune module, to load the VTune module. Nice thing that it has is supports profiling on the host, meaning on the Sandy bridge, and on the mics, and you don't have to do much about it. It has a command line and also a graphical user interface. It knows a lot about OpenMP, for example, but it doesn't know about MPI. But it understands ranks. Okay. So the typical way to use VTune is you compile with -G. So if by now you don't know about -G, we can go back and start over, but I think you already know about it. And then you just run VTune with this command, ample xc-tl, which this is how you usually call it. You have to collect. After collect, you decide which kind of experiment you want to run. For example, in this case, it's hotspots. You might be interested in studying the bandwidth or any other issues that you can imagine. Okay. VTune gives you many options that you can collect, many experiments that you can run. Here, if you type this help collect, it will give you a list of all the things that you can collect. Hotspots is the first one that you always want to run. Okay, it's very useful. These are the different types of collections that we have in Stampede. So once you've run with your collection, you can create a report with dash report, and then you can visualize that with
Aside from hotspots, are there others that you've seen that are popular as far as?
Hotspots is very popular. I can tell you the ones that I like. Okay, I like concurrency if you have OpenMP. Bandwidth, I don't personally like it, but some people use it. Hotspots is, as I said, the most common one. Advanced hotspots, I don't even know if we allow users to do that. I don't think so. You have to be root for that usually. So between hotspots and concurrency, you have most of it done. Also for the mic, K and C hotspots. Okay. Those are the main ones. This is how the summary, that is not the most interesting thing ever. compared to other tools where the summary was useful, in VTune is like, don't care about it. This is always the first window that VTune shows, and it's very misleading. You see how down here it has these colors, red, yellow, green. So if you have 16 cores and your code is just running your code is only running in one core, it would say that your code is awful because it's only using one core. It's like, well, it's not awful. I don't care. Don't know. It's just, I know that it's just running in one core. Okay. So forget about this window and go to the next ones, which are the good ones. Okay. You can go to the top-down tree, which is very familiar for many programmers. So it will give you the flow of your code, like the stacks and everything, different frames. And here you can see where the time is being spent in all the different functions that are being called. Okay, we can see in this particular one that we should be able to see that all the time is being spent in this last call. If you really have a lot of time, I mean, you don't have a life, and you really like assembly code, seriously, get yourself alive. You can even have a look at assembly code. Come on, this is everybody's dream, right? Yeah, actually, I've had nightmares about assembly code. Anyway, VTune shows the assembly code that is generated from your code. So you can click on one line of your code and it will show you the assembly code. So it will show you how from one line it went to 40 lines of assembly code. And you know how assembly code works, right? That beast. But yeah, you have that beast inside of VTune. Again, good luck with that. You only do this in very extreme cases, okay? Yeah, otherwise, I wouldn't go there. That shows you, gives you an idea of how powerful VTune can be. And the last one is Tau. Tau is just another beast. There is a great thing about Tau is that when it works, it's the best thing ever. Second thing is that making Tau work is one of the most difficult things in your life, probably. It's even worse than reading assembly code. That's why they even have a thing in Oregon helping people to use Tau. You had to pay them for doing that. Anyway, it's really good. You have to almost be an expert in order to use Tau properly. When you see it running, as I said, when you go to the tutorials, it is really cool. It gives you all the information you can even imagine about your code. I'm not going to go into much detail about it, but all I can tell you is that it supports everything. I mean, right now, it allows you, if you have a Python code that calls a C code, that calls a Fortran code, it will show you the profile, the whole thing, okay? In just one run, it will tell you, you spend this time in Python, and then you spend this time in C, and this time in Fortran, and in this specific function of Python, C, and Fortran.
And it'll do your threads and everything.
Everything. It does everything. It is that crazy. So when I say that this is great, it is really awesome. But in order to get all those things running, you're going to go through some pain, okay? Let's see how well it does. So first, you have your MPI code, right? Well, you're not going to use MPI CC and MPI F90 anymore. Now you're going to use Tau F90 and Tau CC to compile your code. And now you're going to use Tau makefiles, okay? And then, so you have to decide which Tau makefile you are going to use. We have here that we are using, in this case, an ICPC makefile, meaning Intel C++ compiler with MPI, with PAPI counters, because that's what we care about in this particular case. Many times, well, in this folder that you have here in $tau, you will have many of these makefiles. Just deciding which one you want to use is not trivial. And you're just looking at files to be able to compile your code. So in order to get started, you already have to think a lot, okay? So it doesn't get any easier after that, okay? So, okay, let's say you have decided which one you want to use. Now you export your tau makefiles. You want to enjoy PAPI and you want to use the tau metrics, and then you want to set some tau options. I promise this is tau for dummies right now, okay? This is not advanced stuff. Then you say, hey, I'm going to enable tracing. Once you've done that, you try to compile your code. I didn't put it here that you have to compile your code. Compiling your code is not going to be easy, okay? Usually, well, if it compiles, if everything goes okay, you are great. You have usually a very simple code. The reality is that for difficult or complex codes, just compiling your code with tau is going to be difficult for you. You are going to spend a few days compiling your code, okay? But let's say that everything is perfect and that you have your executable. Well, super easy. All you have to do is run it. And then you can have a look at the results with PAPI, okay? And PAPI is going to look like this. And many people come to this window and say, okay, I went through all that pain to get a window that is telling me that that I have 8 CPUs and that I'm running an Intel Xeon, blah, blah, blah. It's okay. I wasted several days of my life. But it's just, there is much more behind that window, okay? We're not going to go through it, but basically, once you open tau or PAPI, I can tell you, you want to click everywhere because there are some windows that will show up when you click on top of node 1 here. So you will go here and click, and you might have a window showing up with more information. Yeah, it's not the best interface ever. Once you get used to it, you will see that you will discover all the extra windows and everything else, and you will see that it gives you all the information that you could think of. But it's not easy to navigate through the windows. Okay, I mean, even the developers agree on this, so I'm not discovering anything new here. It has a 3D plots of your communication and everything. It's just the 3D plots. I wasn't a big fan until I saw it recently working on. I don't remember what the code was, but I was told about these 3D plots are just crap. No one cares about them. But then once you see it for a real example and you understand what the 3D plot is, it's actually really great. Okay.
What is that telling us?
This one, I don't know this particular example actually, but that's the thing. As you can be thinking of right now, that 3D plot doesn't tell me anything at all. And you have to know the problem, and once you understand the problem, the code, it will tell you. It can be the communication. Let me see if I can see it in this case. It's difficult to see. But it can tell you how the MPI task in a 3D talk to each other, how the different ranks talk, how often that happens, a lot of information. So it's very powerful. But yeah, if you see it right here, as we can see it right now, it's not the best thing, okay? We have all type of information that we can get in tables and stuff like that, how the different ranks or how different functions are called, the relationship between them, kind of what GPROF was doing. But GPROF doesn't have a visual environment to show you this, while tau has it. and all kind of metrics that you can think of, okay? Here, we're not going to go into much detail about it, but you can really do anything you can do with PAPI and all the other tools that we saw before, you can do it just in Tau. So just to finish this, so things you do and things you don't do. Well, you have to test every change that you are making in your code. Don't assume, as Carlos said before, that something that you are doing in your code is going to give a good result, an improvement in their performance. That's not the case. We wish it was like that. It's not like that. You have to profile typical cases. Don't give me a profile that says, oh, I profiled this application with this case that no one cares about, and the performance is really great. It's like, and no one cares about that one, okay? Your normal case is really bad. Give me the normal case. Of course, you have to compile with optimization flags when doing this. Many times, just by compiling with O3 X host and not much more, you get good performance. So remember to do that. And a thing that you don't have to do, well, if you have all the time in the world, you're just doing this for fun, you can do this for the rest of your life. Again, some people don't have a life. But normally, you want to go home or you want to go to sleep at some point. So you will have to stop, okay? Or you have projects to work and your boss is not going to allow you to work on this for the rest of your life. So at some point you have to stop. When do you stop? It depends on what you want to achieve or the time that you have. And those are all the tools that we have here available. There are other tools. I already mentioned Valgrind, which is really powerful. It's really popular. I also mentioned MPI, that we also have it available in Stampede. It's very similar to IPM and the stats that you can get from Intel MPI. And something also, another one that is very powerful is Scalaska, which is very similar to Tau. It's a little bit easier to use than Tau, but the results that you get from Tau are better. Okay, we don't have Scalaska in our system. Okay, and that's it. That concludes our tutorial, our 2-day tutorial. As I mentioned before, we have some labs for debugging that you can follow the slides for that. Basically, all the solution is in the slides that we already went through, so it's very easy to follow. And that's all. Thank you very much for your attention, and we hope you enjoyed it and that you learned something from it. And we hope to see you in our next tutorials.